This is Physics 2211 Lab 5, the following slinky. Purpose is to observe the motion of a stretched slinky dropped from static equilibrium. Things to know beforehand. Newton's second law, which says the net force is equal to change of momentum over change in time. Which you can derive the velocity update formula, which states the final velocity is equal to initial velocity plus net force divided by mass times change in time. And also the position update formula, which says the initial position is the final position is equal to initial position plus the average velocity times change in time. In this system, the system is the slinky, and the surroundings is everything else. In this scenario, the forces acting upon the slinky will be the force of gravity plus the drag force plus the force in the slinky. The force of the gravity is just obviously mass times gravity. Drag force will be the proportionality constant times v squared. So here's my tracker system. I set the axis origin to where the slinky was, and starting at the ground. I set the calibration stick to 1.83 meters because I said this dude right here looks like he's 1.83 meters. So then I track the point of the slinky at the bottom, as you can see right here. Then as I let it go, you can see for the first moments the bottom of the slinky doesn't move, and then it free falls and then until it hits the ground. The reason that the bottom of the slinky won't move is because when it's in that position before the slinky collapses upon itself, there's tension pointing upward that counteracts the force of gravity. So until there's no more tension, which is when the thing collapses upon itself, it will stay there. But once there is no more tension, it starts falling itself, then we get drag force added to it. So my initial code, I had the initial mass is 0.5 kg, initial position 0.576, and then 0. I got that from my tracker video. The initial velocity is 0 because we're dropping the slinky from rest. Gravity 9.8 obviously, and I got the proportionality constant to be 2.59. So this 0.2 right here is before it collapsed on itself. This is the force of gravity, W, or weight, and then Ft is force of tension. Since this is before it collapsed on itself, the net force will be the gravity plus the force of tension. The gravity is negative because gravity is trying to attract the thing to the ground. And then we have the velocity update formula and the position update formula here. This is for after the system has collapsed upon itself. There's no more tension force anymore. Now it'll be the force of gravity plus the drag force added together. And here we have the velocity update formula. Now we have the position update formula still. Afterwards, we get a position time graph that looks like this. As you can see, it didn't quite get to that 0 that we wanted. The reasons for this could be because we didn't really know the exact mass or height of the system. possible tracking errors by me. And there could be other things acting upon the system.